Dear students, let us continue our video lectures on Advanced Digital Signal Processing course. I'm sharing the screen. In this video lecture, let us continue our discussion on discrete Fourier series to discrete Fourier transform. In the previous video lectures, we have seen how discrete Fourier series is related to discrete time Fourier transform. So if we recap, if x of n is a time domain sequence, discrete time domain sequence of m samples, okay, and if we take discrete time Fourier transform for it, what we get is x of e power j omega, that is discrete time Fourier transform of x of n. And now if we sample this discrete time Fourier transform at n different locations, equally spaced locations, that is 2 pi by n distinct locations in frequency domain, since the frequency in the frequency domain x of e power j omega is periodic with period 2 pi, and hence it can be thought of as spanning over 0 to 2 pi, right? And in Z domain, if you plot, as discussed in the previous video lecture, if we sketch this in Z domain, what we are doing through this sampling procedure is to take the samples in frequency domain which are at this location, okay, this location, and which are how much apart? Which are 2 pi by n apart. Okay, these samples are 2 pi by n apart. And how many samples we are taking? Total n samples ranging from 0 to n minus 1. Okay, the number of samples. So this is x of n minus 1, that is x of e power j omega sampled at omega equal to 2 pi by n into n minus 1 here. Okay, similarly the other samples we will get. Fine. Okay, so the magnitude of the samples are on the z-axis, which are not shown here. Okay, these are shown in z, since x of e power j omega is a complex number, and we are showing in z plane. This is unit magnitude, unit circle. Okay, so the radius here is 1, you can assume, and mod z is equal to 1 for this circle I have plotted, and the x of e power j omega values will be on the z-axis, right? So the magnitudes will be on z-axis. Okay, and if you do this sampling in frequency domain, okay, if you do the sampling in frequency domain, so what does it happen? The implication of this is to have x of k, x tilde of k, because this is periodic, this is also periodic, fine, and the inverse Fourier transform or inverse discrete time Fourier series gives rise to x tilde of k, x tilde of n, sorry, right, x tilde of n. And how does this x tilde of n relates to this initial x of n is, how is it related? X tilde of n can be written in terms of the initial x of n, x of n minus r n, because we have taken n samples in frequency domain. Okay, So these x tilde of n of length, okay, of period capital N. Okay, it will repeat, keep repeating at capital N period since there are n samples, and the R is from -∞ to ∞. It keep repeating. Since x of n initially is of m samples, what will happen during this process of sampling in frequency domain? There may be time domain aliasing. Okay, there is a possibility of, okay, if m is greater than n, that means the number of samples here are lesser than the initial number of samples of x of n we have taken, then time domain aliasing happens. Okay, else what will happen? X of n, okay, else what we can do? X of n can be extracted from where? From one period of x tilde of n, right? In this case, this is the case. Else means what is the case here? Here the situation is, since, okay, m is less than or equal to n, right? So the repetition is happening with n, period n. The sequence is of length m, so you can easily extract the sequence x of n from x tilde of n, right? This is what we have discussed in the previous video lecture. Okay, now consider a special case for this. Okay, consider a special case. So what is the special case? We want to consider a case where let m equal to n. Okay, so if m equal to n, what does happen? X of n can be extracted exactly from one period of x tilde of n, and there is aliasing just avoided. Okay, so say for example, I will just for illustration, let us take a small example. Assume that I started with a small signal like this. Okay, and 0, 1, 2, only 3 sample sequence. Here m is equal to 3. Okay, right? And since we made m equal to n, assume that x of e power j omega is also sampled at 3 equidistant points. Okay, so we have sampled x of e power j omega at 3 equidistant points. Okay, so given this, so now I would like to sketch. Okay, we would like to sketch how x of, okay, x tilde of n looks like. Okay, this is what we had is x of n, and we want to now sketch, okay, x tilde of n. So let this be 0, 1, 2, 3, 4, 5, 6, and so on. Similarly here, -1, -2, -3. See, what is the nature of x tilde of n? X tilde of n is periodic. Okay, so it should keep repeating. Sorry, we missed -1, 2, 3, and -4. Okay, so let this, we start here with 3, magnitude 3. Okay, let this be magnitude 3. Okay, let this be magnitude 3 and 2 and 1. Okay, and this is what we have here is x of n. We started with x of n. Okay, well, let x of n be this. Okay, this is example. What we are discussing is an example, right? So now let us see how does the x tilde of n. So 3, 2, 1. And where does the repetition starts? See, m is the length of the sequence, x of n. And where does the repetition start? N equal to, so x of n gets repeated. You can see here, x of n gets repeated at n. So I should, whatever I have 0 will again come at 3 because n equal to capital N equal to 3. Okay, so in this case, n equal to 3. Okay, imply it start repeating at 3. Right? Again, it start repeating at 2n, that is at 6. Fine, and then 3n and so on. Okay, and similarly, it start repeating at -3, right? And hence you will have like this, right? And -6 and so on. Okay, so this is x. What is that we have plotted here? What we have plotted here is x tilde of n. Okay, from x of n in our hand. Okay, so we have taken x of n and plotted x tilde of n. Now, if we want to get back x of n, what can we do? Simply x of n is, okay. Simply we can take one period. Okay, take one period of it to get one period. This itself can be denoted as x of n. So in case if we have a special case of n equal to m, okay, what does it conclude? This implies that, what does this imply? This implies that in this special case, okay, where n equal to m, we can extract x tilde of n. So if n equal to m or m equal to n, x of n is equal to one period of x tilde of n, right? Fine, very good. So is there any other observation we can make? See, if I find now the Fourier transform of x tilde of n, what are discrete Fourier series, because it's a periodic sequence. Okay, what I get is, okay, DFS. Okay, this is DFS. What I get is x tilde of k. Now, if I see one period of, okay, x tilde of k, how does it look like? It looks like exactly, okay, it looks, it also has 3 samples. Okay, the number of samples we have in time domain and in frequency domain then will be same. Okay, and in that case, let us write the equations, and if we consider only one period while writing the discrete aperiodic sequence and its frequency domain representation, that is referred to as discrete Fourier transform. Okay, in general, so where we started with some x of n. Okay, this is aperiodic. Okay, discrete sequence. Okay, this is where we started with. Somehow we got x of e power j omega. Okay, and then we sampled it. Okay, with number of samples n is equal to m. Okay, in under this special case, and we have got from here is equal to x tilde of k with period, okay, n. Now, if we write the expression between x tilde of k and x tilde of n, x tilde of k is equal to x tilde. So if we want to get the frequency domain representation, okay, what we had is, okay, n is equal to 0 to n minus 1. Similarly, if you want to get back this x tilde of n, what we do is projection of these frequency quotients onto the inverse of complex exponential basis. Okay, earlier basis. 0 to n minus 1, as we said, it's periodic in k as well, right? And 1 by n. Fine. So now the question is, given this, we have seen that this is the case where we started with, okay, when x tilde of n is periodic. Okay, when we start x tilde of n with x tilde of n periodic. Okay, this is the case. However, now if we start x of n being a periodic sequence, the question is, can I still have discrete frequency quotients instead of having discrete time Fourier transform, which is a continuous frequency representation? Okay. The question is, can I have for a periodic sequence for a periodic x of n discrete representation in frequency domain? Okay, that is the question. For an aperiodic discrete sequence x of n, can we have a discrete representation in frequency domain? Previously, through DTFT, what we had is only a continuous frequency representation. Okay? Through DTFT, we only had the Fourier transform of x of n. This Fourier means discrete time Fourier transform of x of n being x of e power j omega. Okay, continuous spectrum. But what is the limitation of this continuous spectrum? If we have continuous spectrum in frequency domain, or the representation of continuous representation in frequency domain, what is the limitation we have? The limitation is that we can't represent the frequency domain appropriately with the computer. That is one limitation. Second limitation, see, if I can get back this x of n, the aperiodic discrete time sequence, completely with only just 3 quotients in frequency domain, why should I take the continuous representation x of e power j omega at all? Okay, why should I go for discrete time like discrete time Fourier transform? Okay, so here the question now is, if I give you simply x tilde of k, one period of x tilde of k, these 3 samples. Now the question is, can we get back x of n or not? See here. So if we have x tilde of k, fine. If we have x tilde of k, one period of x tilde of k alone, that is x tilde of x of k we assume. So let we define. So the question now is, can't we get back x of n, this is aperiodic, from single period, okay, of x tilde of k in example discussed, or in general? Okay, this is the question. Fine. If we can get back if we can get back x of n from just one period of x tilde of k, we may refer to as x of k. Okay. What is the need for continuous representation? There is no need, right? Okay. If we can say one period of x tilde of k as x of k, and that is good enough. Okay, frequency representation for x of n, and x of n can be completely reprojected or reconstructed from x of k without need of, okay, continuous representation x of e power j omega. Okay, continuous omega representation. Okay, fine. So in that case, we would prefer that, right? So let us see in this case, will we be able to get back? If I give you only this, we can anyway get x tilde of k. Once we get x tilde of k, okay, we can write from x tilde of k, okay, what we have here, we can apply discrete Fourier series. Okay, x tilde of k we get from the earlier example, and assume that I have applied. What I get is x tilde of n, right? As you have seen, the inverse discrete Fourier series is x tilde of n, and x of n is just one period of it. Okay, so it shows or proves that in case if the length of the aperiodic sequence is lesser than or equal to the number of samples I take in frequency domain, there is no need to have the continuous representation of the frequency information. Okay, or discrete time Fourier transform is not needed. One period of x tilde of k is good enough to store even in frequency domain, and from that we can get back the x of n, a periodic sequence, right? So that means you can just take one period of this to get x of n. Okay, from this x tilde of n where there is a discrete is enough. Okay, so in this case, so x tilde of k itself is good enough. Okay, no need of this. Fine. So what I am trying to convey here is, so if, okay, if, okay, if, let me use a light color here. If m is, okay, less than or equal to n, okay, then x tilde of k is enough to get x of n. Okay, that's what I'm trying. Okay, between these two, okay, this is good enough. Fine. No need of x of e power j omega, right? Okay, that's what we have discussed now. So the discussion now, after the discussion, what we boil down to is, okay, if you have a discrete representation in frequency domain, just k samples or n samples, okay, n samples in frequency domain, those are good enough to get x of n in time domain, and those n has to be greater than or equal to m. So in optimal case, the number of samples in frequency domain has to be exactly equal to the number of samples in time domain. Okay, so in that case there is no need. So we'll just rewrite here the same thing. So we have x of n, okay, m samples, okay, and then we have taken discrete time Fourier transform to get continuous representation of frequency, which we are familiar for a periodic signal. Okay, and then if we do now sampling with n samples, okay, what we get is x tilde of k, and right, and from this what we get is x tilde of this IDFS is x tilde of n, which is summation x of n minus Rn, okay, r equal to minus infinity to infinity, right? So what this indicates is, okay, gives in some sense, gives x of n back optimally if m is less than or equal to n, number of frequency domain. Okay, and no need of x of e power j omega, continuous representation, continuous frequency representation. Okay, x of e power j omega, right? So it's good enough just to go with 3 samples. If x of n starts with 3 samples, why should we have uncountable number of samples while storing x of e power j omega? Okay, so this enables a very great move in the frequency domain representation for discrete aperiodic sequences, because in the real situations, many of the signals are aperiodic and discrete. For processing with computer, we make them discrete. Okay, so it is very natural and very frequently occurring sequences in for processing in digital signal processing or discrete aperiodic sequence, and hence this discrete Fourier transform, which I am now discussing, is one of the the widely used transform for the time domain to frequency domain analysis of signals. Okay, so now let us write. So if we now consider only one period of it, okay, so the same set of equations which we have here also are valid. Fine, because you get back this x of n, right? So now what? So just replacing the x of e power j omega here with x of k, we can write the same set of equations. Let me write, since we have initially written those equations from discrete time for a transform, we can easily take one period of this and get this x of k, which is only one period in frequency domain, and from that one period we can get back x of n, again one period in discrete time signal. Okay, sequence. So let us write the discrete Fourier transform equations. Okay, so how does they look now? So we have now assumed that the sequence is obtained already. So only one period of x of n. Okay, it's a periodic sequence. Okay, so we have actually a periodic x of n, and then same basis functions we use. Okay, and n is equal to 0 to n minus 1. Let this sequence length itself now be n. Okay, m equal to n. Okay, so the assumption here is m equal to n, because m can be less than n, but we don't gain by taking more samples in frequency domain, as just taking n like m samples is good enough. Okay, so given this condition, what are the minimal number of samples with which we can get back this x of n? If one asks, it is m equal to n, right? You can't take less than m because there is a time domain aliasing. But however, if you take m equal to n, you can get back the signal back, as we have seen in this first example, right? So now in this, you can see that what you get is x of k. What is this x of k? This x of k can be considered as one period of x tilde of k, right? And similarly, where does this relation has come? Assuming that there is an underlying periodic sequence is periodic with x of n being, okay, being what? One period of it. Okay, so these are the two two conditions or two assumptions while writing these expressions. Okay, because the periodicity of the frequency coefficients cannot be neglected. So even if you take a discrete aperiodic sequence here, okay, it should be periodic, but we are not showing it explicitly. Why? Because we assume that this is one period of this periodic sequence x tilde of k, right? And for doing this for writing these relationships, we are assuming this aperiodic sequence x of n is virtually a period of a periodic sequence. Okay, x tilde of n, to enable us to write these equations. And there is a frequency domain sampling happening, and through that you have got x tilde of x of k, right? One in frequency domain. So given this x of k now, to get back or the reconstruct the x of n, the periodic signal, what we do is project onto the basis functions e power j 2 pi n, and k is equal to 0 to n minus 1 again, and 1 by n. Same relations hold here, right? So these equations now, if you see, these are looking very neat, and they are applied for aperiodic x of n. Okay, so x of n here is aperiodic, though it is assumed to be a one period of a periodic sequence x tilde of n, right? Okay, right. So please note that these equations originated from DFS. However, now you can apply the same relations, whatever we have been discussing, for all the aperiodic sequences. Okay, so you need not now bother to write every time the periodic sequence and then apply these relations. These relations are now applicable to analyze the aperiodic sequences directly. Okay, because the underlying theory enables us to go from periodic sequence to aperiodic sequence. Okay, so now let us take some small examples and properties. So the examples I will not discuss much, but I will just mention and leave. See, we have taken some examples. Okay. So what we were discussing here is sampling in frequency domain. Sampling DFT, DTFT to DFT, to write DFT. Okay, this is what we have discussed here. Okay, so if you feel this is clumsy, you can leave. This anyway is mentioned in the subsequent slides. Okay, let's leave it. Okay, so here what we have discussed is how DFS is related to DTFT. Okay, relation between DFT, discrete Fourier series, okay, and then we have written here the DFT equations. Okay, fine. Okay, so let us see one example. We will not be solving the whole example, but I will just mention. So let's assume that x of n. Here now we can mention the sequences as say x of n is just delta n. No need to mention it as periodic delta trine and so on, because it's not periodic sequence. I'm taking a periodic sequence. Now what I want to find is x of k. I no need to write here x tilde and so on while solving. So x of k, so I just want to get the frequency representation is x of n e power minus j 2 pi n nk, right? And then n is equal to 0 to n minus 1, and this is equal to 1 simply. So this one is for, so here we assume that the length of sequence here is 1 here. So it means that, so if I take x of n of I can put any length m equal to 10. If I put here also, the number of samples in this also are also 10. So if I consider just say n equal to 10, that means n equal to 10 means how will be x of n? To sketch, it will be like this. So it is 1 here, at 0 location, and then 0, 0, 0, 0, 0, 0, 0. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is the sequence. That's all. It stops here. It doesn't repeat. Okay, so this is n equal to n x of n. X of n sequence of length. Here we say it's of length n, not periodic with n. Okay, and hence how will be, this is x of n, how will be x of k? If we sketch x of k, how will it be? It is 1 for all, say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It will have the same length. Again n equal to 10. Please note that the sequence lengths are same here. Okay, so I have not written explicitly here, but here please note that k is 0 to n minus 1. Because the number of samples we take and in frequency domain and the sequence length are same. Okay, please note that. N anyway is ranging from 0 to n minus 1. Okay, so that is the crisp understanding of DFS, DTFT to DFT, right? Okay, so now this also will have n samples. So no need to bring in all the periodicity aspects and so on. You can simply say that it is of length 10. Okay, no repetitions, nothing. Okay, so this is what we have plotted here is x of k, no tildes and so on, of length. Okay, length 10, that's all. Okay, no negative samples and so on. Okay, similarly we can take another example. This is example 1. Okay, example 2. See, let us take the same examples. We can take anyway different examples, but let us take same example to understand the consequences. See, let x of n now be u of n minus u of n minus 5. Okay, that means what? Let us take this is only x of n. Okay, so that means how will be x of n? So 1, 1, 1, 1, 1, 0, 1, 2, 3, 4. Okay, and say we say that n equal to 0 to 10. Okay, again take length 10. Okay, you can also take length 4, but I think let us take length 10. 5, 6, 7, 8, 9. Okay, this is the sequence x of n. Right now, if you want to find out discrete Fourier transform for it, simply the frequency representation. See, what we have is 1 for, okay, e power minus j 2 pi by 10. Okay, n is 10 here. Please note that. N k and n varying from 0 to 4. Okay, and this give rise to, you can simplify this. Okay, this is n, right? So you will get in k. So you finally see that e power minus j 2 pi by 10 into n by 2, that is capital N by 2, that is 5. Okay, into n is what? Oh, 5, n1 by 2, 5 by 2. Okay, the number of samples by 2 into e power. Just check it. I'm writing from previous discussions we had. 2 pi by 10 into n plus 1 5 by 2. I think this is 4. This is n by 2. Okay, and then sine 5 by 2 into k, because this is now a function of k, right? By sine 2 pi by 10 into 1 by 2 into k. Okay, this I have directly written, but you can compute the summation and write it. And the values of k vary from this sinc function. Okay, and the values of k vary from where to where. K ranges from 0 to 10 here. Okay, 0 to 9 here, because the sequence length is 10. Okay, same as that of the time domain sequence length. Okay, and if you sketch it, how will it be? If you sketch it, it is a sinc function. So if there is a continuous sinc function in continuous domain, continuous time domain, then these will form as samples of it. Okay, we will not exactly bother about the values and so on. Okay, but I will just roughly plot. Okay, let's move on. So here is 0, and where does the first at pi sin pi, the first 0 occurs. Okay, at 0 the value will be, okay, you can see that the value is 1. Okay, and then where does the first 0 occurs? So when it is pi, and hence k has to be equal to 2. Okay, k equal to 2. Okay, k equal to 1 here, minus 2 here, assume that roughly, and minus 1 here, and again at 2 pi. So k equal to 4 here, assume that it is 4. Okay, and this is 3, and this is minus 3, minus 4. Okay, minus 4 if you put it here, again yeah, it's 2 pi, right? So like that. So you can see that these are samples. So let me sketch with different color just to have. And how many samples do we have? We have only, how many samples do we have? We have 10 samples. So based on this way, up to where will it go? So 0, 1, 2, 3, 4. Okay, and my, okay, so I think 0 will start from here. So minus 4, right? So 0 will start from here. If 0 starts here, 0 for discrete signal, 2, 1. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 9. Sorry. 6, 7, 8, 9, 10. Okay, I hope this is correct, but anyway, suggest you to check once. But the concept here is the discrete Fourier series coefficients, which we have plotted in black, okay, or sampled version of the continuous time, say the discrete, continuous spectrum in frequency domain x of e power j omega. Okay, they will become. Here 2 pi by 10 into k, right? And k is varying from k equal to up to 10. Fine, I'm leaving this problem here. So I suggest you to work out and figure out if there is any delay is not properly taken or any small issues here. Okay, fine. Let us move on to the discussion on the properties of discrete time Fourier transform. How do they differ with respect to the discrete Fourier series properties? Okay, or how they what is the similarity between the properties of discrete Fourier series, discrete Fourier transform, and discrete time Fourier transform? Okay, so let us consider first a sequence. Assume that I have an x tilde of n. Okay, and what did we say? If we want shifting property, Okay, well, let us understand the time shifting. Okay, so if I do that shifting, okay, that means delay. By n naught. Okay, if I delay by n naught, what we have is x tilde of n minus n naught. That means the whole periodic sequence, okay, gets shifted like this. Okay, so so instead of, say, for example, if I have a sequence 0, okay, same sequence let us take for ease of 2. No, sorry. 1, 2. Okay. Similarly, again here, assume that same sequence. Okay, 0. So this is our periodic sequence, right? I will not be sketching all the periods, but you can assume 3, 4, 5. -1, -2, -3. Okay. So now what we are doing? So let n naught is equal to 1. Okay, we are just shifting it by 1 unit. Fine. So if I shift this by 1 unit, okay, where how will be x tilde of, this is x tilde of n, how will be x tilde of n minus n naught? So let us assume that this is 0 now. Okay, so there is a shift by 1 unit, and hence this will occur now. Instead of occurring at 0, now it will occur at 1 time instant 1. Okay, that means it, the initial, this 2 magnitude 2 will occur at time instant 1 instead of 0, right? And then this will occur here and this will occur here, 2 and 3, right? And since it's a shift to periodic sequence, okay, the previous whatever I had at -1 will come here. Okay, and then -2 will come here, -3 will come here. This is at -1, -2 now. Okay, so let us sketch in the same duration which I have sketched here. Okay, 3, 4, and 5. Okay, where you have here the shifted sequence. Okay, now here this is x tilde of n minus 1. Okay, and this is x tilde of n, right? So now what we wish to do is, see, as we have defined discrete Fourier transform just based on n samples, okay, without worrying about the periodicity, without bringing in the periodic aspects, we also would like to see what happens in one period here. So if you see one period here, okay, this is this one period, okay, so this is one period. So within this period, one period, if I sketch now, what I have will be x of n. Okay, so x of n for this is simply 3, 2, 1, 0, 1, 2. Here I just want to see what is x of n minus 1, but I will not write the notation completely now. Okay, let us see if what notation should we put. So I just want to take one period of it again, because what will happen, our relation in DFT is guided by the periodic sequence. So the sampling happens in frequency domain, and hence it implicitly imposes a periodic nature in time domain as well. Okay, even though we start with a periodic sequence, let us now assume that we have started with this and got this. Okay, got this. Fine, and then we applied this delay. Okay, delay by 1 unit. Okay, and then we sketched this and now we want to sketch what will happen to this x dash of n, you can assume. Okay, after doing this process, because the equations are guided by discrete like time Fourier transform and periodicity, we should consider the periodic sequence behind and analyze what will happen to the time domain in that period 0 to n, because we sample again in frequency domain means we take only one period. So how will it be? You can see that this is now, see, I would like to take same region, 0, 1, 2, same 3 samples. Okay, so how are they? Right. So 1, 3, and 2. Here 3 to 1. Okay. So now can you see? Can you tell how do we get this sequence from this x of n? X of n dash of n is related to x of n by what? You can see, like when we discussed about the frequency domain sampling. Okay, since for any periodic sequences, okay, shifting means what? A periodic sequence, this can be visualized, okay, as samples on regular intervals of a circle. Okay, assume that I have 3 samples, right? So the first sample may be here, okay, n equal to 0, and second sample n equal to 1 may be here, okay, n equal to 1, and n equal to 3 may be here. Okay, something like this. Now 120 degrees apart. Okay, n equal to 3. I only have 3 samples. Now shifting the periodic sequence means, okay, instead of starting from here, okay, so I will start from here. Okay, instead of starting from here, so here, say this is, if I start from here for x of n, whereas we start from for x of n minus 1, for x of n minus x tilde of n minus 1, okay, start from here, right? So that's what happens. Okay, so if you start from here, what is happening? This can be considered as a circular shift. You have done like this rather than starting from here. Okay, so you have now done like this. So it is a circular shift. Okay, you started with a circular shift. So how do we relate this? X dash of n is equal to x of n minus, how, like x of n minus 1, right? Where we have the value that doesn't fit in 0 to n region, n minus 1 regions. Okay, so where does the value has come from? It has come from the previous sample. That means, say in case if we have n equal to 0, if we take here, so that means at 0 we will have minus 1, but the sample has come from, okay, the corresponding sample in the previous minus 1. That means n minus 1. Okay, so this is operation is referred to as modulo operation. Okay, so when it goes out of it, you can consider it as remainder, okay, with respect to the capital N. Okay, and that is n minus 1. Okay, whenever there is a negative number, we can directly take it as n minus 1. And this is what establishes the relation while shifting. Okay, so how do we write? So if you delay this by like this, in time discrete, say if you want to write in one period, how do we write is, this implies, okay, in a periodic sequence, in corresponding a periodic, we can say sequence, what does it imply? X of n minus x of n delay by n naught, okay, is x of n minus n naught modulo n. Because the sequence is length n, okay, and length n. Okay, always we start from 0 and the length is n. Okay, this is how we define delay for writing when we discuss in the context of discrete Fourier transform. Okay, because discrete Fourier transform underlyingly assumes periodicity in frequency domain as well as in time domain. Okay. In discussions of DFS, in DFT discussions. Okay, if you want to apply DFT, okay, you only, what we do is only circular shift, not a linear shift. Okay, this we should be clear. Fine. Okay, so now let us move on. So this is how we define the time domain shift or delay itself. Okay, to maintain the sequence length to be same. And also to take the underlying guidance of time periodicity. Now let us bring in how to find, okay, delay. If we have delay in, so properties further we discuss. If there is a delay, x of n minus n naught here, that is, okay, and because modulo n, fine. So if it is x of negative number means minus 1 is equal to, so if you, in the previous discussions, please note, okay, see here, we write with x of minus 1, okay, x of minus 1 here is equal to x of modulo n is equal to n minus 1. Okay, please note that. Fine, that we want to get the whole information from this x of n itself, which is with us, okay, for shifting and so on. Okay, considering the underlying periodicity for DFT, discussion of DFT. Okay, please note this. Right, so now this, if we take DFT, discrete Fourier transform, okay, what does it happen? So what does it happen? Exactly what does happen for the discrete Fourier series will happen here. So what we have written? So for discrete Fourier series, we have written that x of n minus n naught. Okay, if you take discrete Fourier series, okay, what we have written is x tilde of k into e power minus j 2 pi n into n naught into k. Okay, this is what we have written at that time. So same thing will happen even here, except that we have the same set of quotients. Okay, here this also of length n and e power minus j 2 pi by n and not k, because this number of samples of this in one period, okay, is equal to the number of samples of this sequence itself now. Okay, right. So all the properties look similar nature, have the similar nature, except that wherever there is a shift involved, either in time domain or in frequency domain, there will be the modulo n operation there to take care of the periodicity, underlying periodicity of the, while writing the DFT expressions, and also to take this, this enables us to take the samples conveniently from the n length sequence. Okay, so let us write another property. Let this be x of n. We have exponential sequence. Okay, multiplying the time domain sequence now. We want to find discrete Fourier transform. Let us write this time directly. How will it be? X tilde of k minus k naught. Fine, but what we want to restrict the whole information to be one period, and hence it is n. Is this tilde required? No tilde will be there, because the number of samples of the original sequence or n sequence, n sample sequence. Okay, then frequency quotients. Okay, so please note that this enables us to write the duality property also comfortably. Please note here we have the modulo n operation in frequency domain because the quotients here may go negative and so on. May go out of the range of 0 to n minus 1. Okay, in that case, modulo n operation enables us to write the corresponding quotients effectively. Okay, and now let us write the duality property as well. So what did the duality property in and this is shifting property. Okay, and this is anyway modulation, time domain modulation. Okay, so it enables, what does the duality property enables us? To write conveniently the frequency domain to time domain or time domain to frequency domain, like transformations. Now assume that, so let us take the same if you remember the duality expression in like DFS, how did we write? We have written that if we take initially the frequency quotients to time domain, okay, and then apply the discrete Fourier series, here it is for a discrete Fourier transform, what we get is n times x of minus k. Okay, so that means if we have with us, okay, x of DFT of x of n is equal to x of k, then okay, we can conveniently write the inverse discrete Fourier transform using duality property. Okay, or say you can, if you have the DFT, if you have with us IDFT of x of k equal to x of n, we can easily write DFT. Okay, so fine. So you can also see the same examples and how does this is applied there. Right. Now let us discuss one more important property and then the one or two more important properties. So say if we have a sequence, see x of n, x tilde of n, okay, and if we flip the sequence, how do we write it? X tilde of minus n. We want to see what's the implication of flipping, okay, x of n, and for the flipped x of n, we wish to take DFT and so on to analyze the frequency domain information of this aperiodic sequence. Okay, how should we write? X of minus n we can write. However, this sequence is of length n, 0 to length n, that means non-zero for, okay, non-zero for 0 to n minus 1, and hence we wish to have even this non-zero for 0 to n minus 1 or length n for effective processing. Okay, so this comes from the periodicity, so you can take, instead of taking one period, you can take the other period of x tilde of n. Okay, this comes from this. Okay, and hence this comes with modulo n operation to take that. Okay, for DFT. Okay, so now let us see how do we write x even of n. Usually for any aperiodic sequence, when we do with DTFT, how did we write x even of n? X of n plus x of minus n by 2. Okay, if it is complex sequence, x star of minus n by 2. Okay, this is how we define even sequence. While DTFT computations. Okay, but however, here we would like to, in DFT computations, okay, what should we want to do? We want to restrict the whole operation to n samples because the DFT underlyingly assumes a periodicity in the frequency domain and in time domain. Okay, so and hence for DTFT computations, we define modified even sequence as x even. Okay, let even p of n is equal to, how do we define? X of n plus x star of, what should I write here? Minus n modulo capital N, because the length of sequence we have taken to be n. Okay, from here we start to identify what will happen in frequency domain and so on. Okay, so this is the major change. Whenever we do whatever operation we do, we restrict the number of samples to n, and since there is an underlying periodic sequence, we take those n samples which will fall in that duration. Okay, initially we reference or we started with for all DFT computations, right? Okay. Okay, so now let us also write here. Say if we have x even of n, okay, x even, okay, what if we take DTFT? So let us first write the DTFT case, discrete time Fourier transform. Okay, what did we, for even sequence, if we take discrete time Fourier transform, did you remember what is that we get in frequency domain? Assume that there is an x of n initially, for which DTFT is given by x of k. Okay, this is x of, this is, sorry, DTFT. So what should I write here? X of e power j omega. Okay, so now I have constructed an even sequence from this x of n. And then from this, I have taken the discrete time Fourier transform. What is expected to get? The real part of x of e power j omega. Right? Yeah, go back and refer, and it should be the case because, okay, we will write it. So now similarly, in the, if we now take the even sequence, okay, in reference to computing DFT now, right? We want to compute DFT of the even sequence. When we want to compute the even DFT, we should only take this XEP of n, where there is a modulo n operation and the whole signal length, okay, is 0 to n minus 1. Okay, length n. Fine. And that means whatever the operations we perform will be performed in the okay, operations, all the operations will be performed in 0 to n length. So flipped signal being periodic, underlying x tilde of n, it will also have some component in this region, and hence that is only counted. For both the signals, the region in this is counted for writing even sequence. Hope you got the point, because both have an underlying periodic sequence. Okay, this understanding has to be there in background, and this writing can be enough while writing. while calculations. Now what the answer will be? This you can check it to be real part of x of k. Okay, this is the advantage of discrete Fourier transform. You can see that x of k simply what we have. What is x of k? We assume if what is x of k? In case if x of k, sorry, if x of k is what? Discrete Fourier transform of what? Of x of n, right? If we write both, all are n point sequences. Okay, so all here are n point sequences. Okay, please note that all are n point sequences. Okay, this is important observation, and you can see that actually the we can simply write the for this this is the real part of x. Same expressions, whatever same properties, whatever we have defined for discrete time Fourier transform are valid, right? In fact, these are valid even for discrete Fourier series. Okay, except the change that while writing discrete Fourier series, okay, everywhere we write here tilde. Okay, x tilde when we write. So if you want to write discrete Fourier series, okay, x tilde of even part of n is equal to x tilde of n plus x tilde of minus n. We can write it here because even the we have from minus infinity to infinity. So hope you have seen the discussion that we had on writing the discrete Fourier transform for even sequence of length n, and how DFT can be used in that situation. Okay, so similarly we can write for all the properties that we have had for discrete time Fourier transform follow also for discrete Fourier transform, except the change that whenever there is a sequence goes out of 0 to n range, there is a modulo operation required. Okay, however, there is a small change in some of the properties, especially the convolution to like convolution in time domain to correlate like multiplication frequency domain kind of operations are the properties. Okay, so if we perform operations of convolution or multiplication in time domain, how does they reflect? There, the guidance can be taken from the discrete Fourier series. Okay, that we will discuss in the next video lecture. Thank you.